Our study of soils typically looks at the granular skeleton, in other words, at the soil mass. However, so much depends on the presence of water. For example, the degree of saturation, the availability of space for other substances, the capillary effects, the stiffness of water relative to the compressibility of the skeleton that will generate the excess pore pressure leading to liquefaction. And that is just for the coarser grains. If we want to understand the behavior of clays, then we really need to understand the behavior of water and clay, that interaction. So let's pause for a second to understand water. And today I would like to cover 4 or 5 fundamental concepts. The first one, as you all well know, water is a dipole. That is not enough. We need to recognize that it is vibrating. Furthermore, it's not just a dipole. As you will see, the tail of the water also allows for some coordination, and so we are actually going to look at the tetrahedral structure of the water molecule, leading to what is called hydrogen bond. Finally, today I would like to discuss the fact that water self-ionizes. Let's explore some of the consequences of these concepts. The first one is, let's look at the water molecule. It really looks something like that, where the mean diameter is of the size of 2.7 angstroms. These are the hydrogens, and they are not really sticking out like we see in some simple diagrams. They really look like that, and this is the oxygen, so this is water. But something that is very important is that the hydrogens are not aligned. For example, if I were to draw CO2, this would be carbon, and these are the 2 oxygens. So the CO2 molecule is aligned. However, these ones are at an angle, and that is because they are trying to find the best position with respect to the electrons that are going around the nucleus of the oxygen, and that is where they fit best. So water is a dipole. There are so many implications for water being a dipole, but probably the first one that we should keep in mind that it is because water is a dipole that becomes a great solvent. Why? Because if we have sodium chloride, which looks like that, then water comes, and let's say that this is the chlorine and this is the sodium. Sodium being positive, so the water molecule comes with a tail and sits like that, but in the chlorine, the ears of the water go forward, and as you begin throwing more and more water molecules, they begin creating Coulombian repulsion, which in the end splits the sodium chlorine apart, forming salt water. That is the dissolution of salt ab initio, at the very fundamental level. So water is a great solvent because it is a dipole. If I would put the same salt crystal in carbon tetrachloride, which looks like that one, but like the CO2, but instead of having oxygen, it has a chlorine in 4 directions, totally non-polar, there is absolutely no solubility of salt in that nonpolar molecule. This is critical because this will give rise to life. And we will see why that is the case, but at the beginning is because of the ability to dissolve salts. And it is also critical for the formation of minerals and this dissolution and precipitation, residual soils. All starts by the fact that water is a dipole. The second thing I would like to highlight, that we don't see it in a glass, but water molecules are continuously vibrating and knocking each other and breaking bonds and jumping from one place to the other. They are continuously vibrating. And that is critical in many applications, but it's that activity of water that will become so effective in breaking salts. But the other thing, for example, is if you have a water jar, there are vapor molecules at the top and water molecules in the water, and there is a continuous interaction between the atmosphere and the water, where water molecules jump out into the vapor phase and water from the vapor condense and fall into the liquid phase. That happens also between water and ice. And we couldn't explain many processes like related to hydrate-bearing sediments if we couldn't understand this continuous interaction. Nothing is static at this scale. Now let me mention one more important thing about water being a dipole. When we put water molecules in an electromagnetic field that is oscillating, as the electromagnetic field goes up, it brings the hydrogens to the top. When it goes down, it forces the hydrogens to rotate. And if we do this 2.45 gigahertz, that means times 10 to the 9 times per second, then we have a microwave oven. So microwave oven works because water is a dipole. And as the microwave traverses the water or the potato or the chicken, it forces the water molecules to rotate and break bonds and collide with each other, and therefore heats up the food. But the water has to be liquid. The microwave oven will not work if the water is frozen. In fact, there is another function in the microwave oven to do that, and that is because water is a dipole. But really, the story is a little bit more complex. Imagine that I would send a space shuttle to rotate around a water molecule with a positive test charge. So as it travels around, it will detect repulsion to the hydrogens, attraction to the water, but there will be a couple of points towards the bottom of the water where there is special attraction. And therefore, water is not just a dipole, it has kind of a tetrahedral configuration. And now, if I have a water molecule, another water molecule will come and probably will put the ear in this direction, so there is some interaction at the water molecule, and probably another water molecule will be here in this other configuration. And so we started with the first water molecule here, and we recognize that it's bonding to other water molecules through the tail of it. These are called hydrogen bonds. The implications are critical, and we'll discover them as soon as I clean the board. Summary. Water is a dipole, and it is more complex than that. There are points on the tail of the oxygen. The lone pair of electrons are attracting other water molecules, so other water molecules will be bonding through hydrogen bonds. There are very profound implications. Let's discuss the first one. Let me ask a very weird question. What is the porosity of water? Well, let's start by definition. Porosity is equal to the volume of voids over the volume total. Now, it's difficult to quantify the volume of voids, but the volume total minus the volume of water molecules, that would be a more interesting one, over the volume total. And now, what is the volume that water molecules occupy? So let's consider 1 mole of water. And if we take the atomic mass, 1 mole of water is equal to 16 grams due to the oxygens plus 2 times 1 gram due to the hydrogens. And so this is going to be equal to 18 grams per mole. Now, because water has a density of, so this is the mass of 1 mole. Because water has a density of approximately 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter, this is equivalent to 18 cubic centimeters. So this is the total volume that a mole of water occupies. Now, what is the volume of water that a mole of water occupies? Well, it will be Avogadro's number times the volume of a water molecule. And the volume of a water molecule, you can compute it from the fact that we said that it was about 2.7 angstroms in diameter. So this is 4/3 pi d cubed 2.7 angstroms cubed over 8. And this is Avogadro's number, which is 6.02 times 10 to the 23 molecules per mole. Molecules per mole. So now we know the volume that water occupies, and we know that for 1 mole, and we know the total volume that water occupies for 1 mole. So now we are ready to compute the porosity, and if you put the numbers, it turns out that the porosity of water is 63%, 0.63. This is a concept that is hard to grasp, but the fact is that there are lots of voids in water. And the fact that there are lots of voids in water, it means that we will be able to hide things in these voids. So for example, we can hide gases. We can hide oxygen. We can hide nitrogen. And this is so important because, for example, fish need to breathe. And fish are breathing not because of the oxygen that makes the water molecule, it's because of the dissolved oxygen that is held in the voids of water. 63% porosity. We will see what happens when we add salt. The final thought that I would like to leave with you today is that water molecules, and in general for any atomic systems, molecular systems, they are continuously forming and disaggregating. And so water molecules, H2O, can split into a hydroxyl and a hydrogen. Now, this is not very stable, so when you take 2 of these, actually what you end up forming is a hydronium, which is going to be OH cubed plus another OH. How often does this happen? Well, this self-ionization happens in the order of 10 to the 7 moles per liter of water, which, by the way, we could convert to the number of moles of water, which is 1,000 grams divided 18 grams. So when we take the logarithm of that, the logarithm of 10 to the 7 gives us 7, and that's what we are going to call the pH. When we say that the pH of water is 7, we are referring to the self-ionization of water. And now, if we have more OHs because we have added a hydroxide, or we have less pH because we have added an acid, then we are changing the balance between OHs and hydroniums, or OHs and Hs in water. And that will control mineral dissolution. So please take a look at the follow-up presentation that will dwell and go into further details to explain the implications of these simple concepts on the role of water in soils. To summarize, water is a dipole that it is continuously vibrating. The structure is a little bit more interesting, and the tail helps other hydrogens to bond to a molecule, forming hydrogen bonds. Now, water tends to split in small quantities, and that self-ionization is what is leading to the concept of pH.